Humanity has lived on Earth for thousands of years with the question, is anyone else out there? In the eerie silence of the vast void, this tiny planet seems like just a small, isolated speck among billions of celestial bodies. But it is precisely this that has ignited humanity's desire to search for life beyond the universe. After countless research efforts and various probes, the answer we have received still doesn't satisfy our curiosity. Could we be the only beings existing in this endless universe? Or, somewhere between distant planets, is there another form of life waiting to be discovered? Now, our hope is focused on the Moon's south pole, where eternal darkness and ancient frozen ice may hide the answer to the greatest mystery. Why has this region attracted so much attention? What discoveries in the South Pole have rekindled humanity's faith? Are we on the verge of entering a new era where extraterrestrial life is no longer just a dream? The journey to explore the truth begins now, in today's video. The South Pole of the Moon, the key to extraterrestrial life. The Moon, Earth's only natural satellite, is one of the most familiar celestial bodies to humanity. It is believed to have formed about 4.5 billion years ago after a colossal collision between early Earth and a celestial body roughly the size of Mars, called Theia. From the debris ejected by this collision, the Moon gradually took shape in its orbit. With a radius of about 1,737 kilometers, it is the fifth largest satellite in the solar system and has about 1/6 of Earth's gravitational pull. The Moon's structure consists of three main layers: the crust, the mantle rich in minerals, and the core. Its terrain was shaped by ancient collisions and volcanic activity, creating impact craters, lava plains, and mountains. Due to its unique position, the Moon became the first celestial body humanity studied and explored. Since Neil Armstrong's historic image, humanity has carried out numerous explorations there. As a result, we have almost fully explored this lunar satellite. Most experts and people believe the Moon is not an ideal place for life to develop. However, this view may change in the future as scientists begin to study a special region on this planet, the South Pole. Could this area resemble Earth's frigid South Pole? Why might it change our views about extraterrestrial life? Let's first examine its geographical features. The Moon's south pole is marked by rugged terrain and a high concentration of craters and large basins. These craters are not only massive but also contain many unique features. The most prominent of these is the Aitken Basin, also known as the South Pole Aitken Basin. It is the largest impact crater not only on the Moon but in the entire solar system, with a diameter of about 2,500 kilometers and a depth of 8 kilometers. This basin was likely formed by a massive meteoric collision billions of years ago, revealing deep geological layers beneath the surface. With this feature, studying this area could help humanity better understand the lunar structure, extract resources, and place long-term exploratory equipment. Additionally, the South Pole contains many craters in areas of permanent shadow. Due to the Moon's tilt being only about 1.5 degrees, sunlight never reaches the bottom of these craters. The temperatures in these regions are extremely low, around -240 degrees Celsius, making them ideal for preserving frozen water and volatile compounds for billions of years. Furthermore, the South Pole of the Moon may hold many important resources. One of these is helium-3, a rare isotope accumulated from the solar wind. It is used in thermonuclear reactors as a clean and highly efficient energy source. If we can harness it, humanity will gain access to another vast resource for development. And not only is the Moon's South Pole a treasure trove of minerals, but it also serves as a natural laboratory for scientific research. The craters and materials deep in the Moon's mantle may contain vital samples. By analyzing and studying them, humanity will learn more about the evolution of this natural satellite, as well as the history of Earth and other planets in the solar system. Many compounds in these permanent shadows have been preserved intact, helping to recreate the chemical conditions of the early solar system, conditions Earth can no longer retain due to geological activity. For these reasons, conducting exploration missions to the Moon's south pole has become a necessity. It will mark a major step forward in science, technology, and open up many opportunities for human development in the future. The interest in this special region has led countries and space organizations worldwide to plan missions to explore the Moon. India is one of the countries with such ambitions. As early as the 2000s, the Indian Space Research Organization, ISRO, had plans to develop spacecraft for studying Earth's only natural satellite. The Chandrayaan-1 project, meaning mooncraft in Sanskrit, was born with the goal of mapping the surface, studying minerals, and searching for water ice. This mission began the journey of exploring the south pole of the Moon. On September 28, 2008, Chandrayaan-1 was successfully launched from the Satish Dhawan Space Center in Sriharikota aboard the PSLV-C-11 rocket. After several orbital adjustments, the spacecraft finally entered lunar orbit on November 8. It began a 312-day mission, conducting various experiments and measurements. One of the most significant contributions of Chandrayaan-1 was the discovery of water ice in the Moon's permanent shadow craters at the South Pole. Let's pause for a moment to understand what water ice is. It is water that has been formed over billions of years from various processes. When proton particles from the solar wind interact with metal oxides on the Moon's surface, they form hydrogen, which then combines with oxygen to create water. Also, past collisions with meteors and comets may have brought water to the Moon. In the South Pole region, deep craters create areas of permanent shadow, where sunlight never reaches. The extremely low temperatures have helped preserve water ice in a stable state for long periods. Why is this discovery considered monumental? In fact, finding water ice at the Moon's south pole has profound scientific, economic, and strategic implications for space exploration. It could be processed into drinking water, paving the way for long-term human missions to settle on the Moon. The extraction of water ice could reduce space mission costs, serve as rocket fuel, and provide oxygen for astronauts. Returning to Chandrayaan-1's mission, besides water ice, India's probe also recorded iron-rich compounds and minerals such as olivine and pyroxene, providing valuable data for understanding the Moon's geological structure. It also mapped the South Pole, providing data on temperatures, sunlit areas, and resource extraction potential. This data serves as the foundation for future Indian missions to this special region. 11 years later, ISRO restarted its lunar mission with the goal of reaching the South Pole with Chandrayaan-2. Although it was highly anticipated, the spacecraft crash-landed on the Moon's surface. Not stopping there, India launched Chandrayaan-3, which successfully landed in the South Pole region. With more advanced technology, the Moon's surface appeared rugged with numerous craters scattered across it. From here, India focused more on exploring water ice. In addition to India, the United States also has its own missions to explore the Moon's south pole. Launched on November 16, 2022, Artemis I marked America's impressive return to space leadership efforts. After more than half a century since the Apollo 17 mission, when humans last set foot on the Moon in 1972, this was an uncrewed mission primarily aimed at testing the new Space Launch System and the Orion spacecraft. Artemis I also marked the first step toward a larger ambition, to establish a sustainable human presence on the Moon and lay the groundwork for Mars exploration. Its immediate goal is to send Orion into a distant orbit around the Moon to study the South Pole region of this planet. After 25 days, 10 hours, and 53 minutes, the Artemis I mission has successfully made a significant step forward for humanity. It continues the story of reaching far beyond our world, bringing new discoveries and inspiring future missions. So, what have we learned about the South Pole region of the Moon after all these observations? It remains a big question that scientists still do not have an answer to regarding this special area of the Moon. Is there a possibility of life existing there? With the weather conditions and terrain, the South Pole of the Moon shares many similarities with Antarctica on Earth. Both regions are extremely cold and contain frozen water. Many skeptics question whether life could exist beneath the icy surface. However, on Earth, living organisms have been discovered in the frozen regions of Antarctica and deep volcanic craters. The scientific name for these organisms is extremophiles. These are tiny life forms capable of adapting and thriving in extreme environments. They have been found in many places, such as the ocean floor's volcanic vents, the permanent ice regions of Antarctica, and even in arid deserts without water for centuries. This has shown that life can indeed survive in conditions once thought impossible by science. This opens up the possibility of similar life forms existing at the South Pole of the Moon. However, outer space is a very challenging environment. With its very thin atmosphere and extreme conditions, the Moon is generally inhospitable to life. Yet, the South Pole area is somewhat different. In the permanently shadowed craters at the Moon's South Pole, temperatures could be more stable, as they lack direct sunlight. Thus, life forms like psychrophiles, microorganisms that thrive in cold environments, could potentially exist there. Additionally, the presence of frozen water and ice is a crucial factor for supporting life. Organisms on Earth, such as those living in Antarctica's permanent ice, can use ice as a source of hydration and nutrients. Not stopping there, the Moon lacks an ozone layer to protect from cosmic and solar radiation. However, scientists have found a type of microorganism that can withstand radiation levels thousands of times greater than what humans can tolerate. If they truly exist, these microorganisms could thrive in the harsh environment of the Moon's South Pole. With these arguments, the hypothesis of life existing on Earth's natural satellite has gained considerable support from experts. To strengthen this theory, we must answer another question: how do extremophiles survive at the Moon's South Pole? Unlike Earth, life forms on the Moon would need to have special evolutionary adaptations. First, they would need to develop a protective outer membrane or antioxidant compounds to shield their cells from radiation damage. The DNA repair and recovery systems of these organisms would also need to be enhanced, as radiation and extreme temperatures could cause significant damage. A special adaptation found in many Earth microorganisms to cope with harsh environments is dormancy. In this state, metabolic processes almost completely stop, allowing organisms to survive for centuries in extreme conditions. Additionally, if microorganisms live on the Moon's South Pole, they could use the minerals on the Moon's surface as an energy source. Chemical processes between these microorganisms and the minerals could generate the energy required for survival. Most importantly, if life exists on the Moon, there would be no oxygen to facilitate gas exchange. However, many bacteria on Earth can survive and thrive in anaerobic conditions. For example, anaerobic bacteria use nitrates or sulfates instead of oxygen in their metabolism. Thus, life on the Moon's natural satellite could very well evolve along these lines. Therefore, the theory of extremophiles existing on the Moon's South Pole raises important questions about the potential adaptability and survival of life in the most extreme environments. Based on what we know about extremophiles on Earth, it's possible to imagine that similar mechanisms could support life on the Moon. But is this feasible? To test this hypothesis, scientists would need to employ a range of modern scientific methods combined with advanced space technology. One of the most direct and feasible ways to test the extremophile hypothesis at the Moon's South Pole is to collect soil and rock samples from this region. This approach would provide samples that may contain microorganisms or traces of them. Robots and spacecraft will collect soil from the moon's permanently shadowed craters and return it to Earth. Experts would then use methods such as PCR, DNA analysis, or electron microscopy to look for signs of microorganisms, such as cell structures or nucleic acids. Additionally, scientific analysis would be conducted to detect organic compounds, identifying biological signatures. The moon could contain minerals and inorganic compounds that could support life. Extremophiles could use minerals like sulfides, iron, or other metal compounds as an energy source. Analyzing these minerals in moon samples could help determine whether the environment could support life. Moreover, collecting samples from the moon could utilize biological and microbiological technologies to detect traces of life and the potential for extremophiles to exist in the moon's environment. Using synthetic biology techniques, laboratory simulations would test their survival in moon-like conditions. The entire adaptation, survival, and development process of these organisms would be observed by scientists to draw final conclusions. After testing on Earth, biological sensor technologies will be adapted to spacecraft and exploration robots. This way, experts can conduct tests in the actual moon environment without needing to bring the samples back to Earth. Apart from these methods, analyzing radiation resistance and the ability of microorganisms to endure the moon's extreme conditions would also help confirm the existence of life at the South Pole. Since the moon has a very thin atmosphere, incapable of blocking solar and cosmic radiation, scientists can assess the survival potential of microorganisms in this harsh environment. Special organisms will be cultivated in space environments, simulating high radiation levels in Earth laboratories. Ultraviolet, X-ray, and cosmic radiation will be used to test their survival and evolutionary potential. This will help assess the survival rate of microorganisms in the moon's South Pole conditions. Moreover, confirming the existence of life at the moon's South Pole will need further verification through the presence of organic compounds, especially those associated with biogenic processes. By analyzing lunar soil samples, scientists may detect these compounds or biological traces, showing that microorganisms could have existed or may still exist there. To do so, researchers will use infrared spectroscopy and Raman spectroscopy. Thus, the answer will be quickly discovered. It should be noted that testing the hypothesis of extremophiles on the moon's South Pole is a task that requires advanced technology and complex analytical methods. If traces of life are found, humanity would gain a new perspective on the moon and potentially other extraterrestrial environments. However, the methods mentioned above have certain limitations and could lead to errors if any details are inaccurate. We cannot fully replicate the moon's extreme conditions in a laboratory, nor can we create the radiation and other harsh factors of the space environment in an Earth-based lab. So, how can we confirm the existence of life in this area? Indeed, humanity has only one option: going there to study it firsthand. From here, a series of missions from various space powers are being carried out and will continue to be. One of these is Artemis 3. After the approval of Space Policy Directive I by President Donald Trump in December 2017, this political project was initiated. The most remarkable aspect is that this mission will return humans to the moon for the first time in over 50 years since Neil Armstrong's historic footsteps. NASA has revealed many ambitious goals for the Artemis 3 mission. Astronauts will land at the moon's South Pole to collect soil and rock samples, study the geological structure, and assess the distribution of ice. To achieve this grand mission, NASA is using the SLS, the most powerful rocket ever made, capable of carrying large payloads and providing enough energy to send spacecraft into lunar orbit. Accompanying the astronauts is the modern and safe Orion spacecraft. In addition, the XMU spacesuit has been specially designed to support movement on the moon's surface, especially in challenging areas like the southern pole, which has also been announced. As a result, astronauts will be more flexible in their actions, protected from radiation in the environment of this planet. According to a report released by NASA, the NASA Artemis 3 mission will be launched to the Moon in 2025. Perhaps, in just one more year, humanity will gain deeper insights into this special area. Will life exist at the Moon's southern pole? From the great Artemis 3 mission, NASA scientist Pravin Sasina has put forward a different theory regarding the possibility of microorganisms existing in the natural conditions of the lunar surface. So far, most of us agree that the Moon is not suitable for life to thrive. However, if Orion and the astronauts successfully land on the southern pole, microorganisms carried from Earth might be able to survive. This seemingly crazy hypothesis has actually been considered, and experts have recognized several convincing points. Sasina proposed that areas within the permanently dark regions of the Moon's southern pole, where there is no sunlight and protection from solar radiation, might be ideal environments for microorganisms. These regions could shield microorganisms from extreme temperatures and strong solar radiation, allowing them to survive in this harsh environment. A key point in Sasina's hypothesis is the study of extremophiles on Earth. As mentioned above, these microorganisms have shown miraculous survival abilities in extreme environments such as the deep ocean, icy regions, and even hydrothermal vents. According to Sasina, they could survive under similar conditions on the Moon if brought there by human missions. This becomes even more plausible when considering the presence of water ice at the Moon's southern pole. Recent studies suggest that craters in the Moon's southern pole may contain water ice in the permanently dark areas, where there is no sunlight and protection from radiation. This water ice is not only a valuable resource for future space missions but could also provide a suitable environment for microorganisms to exist. Although Sasina's idea remains a hypothesis and there is no direct evidence to support it, it opens up different possibilities for exploring life in extreme environments. Perhaps in the future, when Artemis 3 succeeds, this argument will be verified. When Sasina's hypothesis was released, many scientists believed that he was too far-fetched. They focused on finding evidence rather than an argument that sounds reasonable but is unconvincing. Hugh Graham, an organic geochemist at NASA's Goddard Space Center, is one of them. She agrees that while meteorites may not be the most reliable means of carrying microorganisms, manned missions like the Artemis program could unknowingly transport microorganism spores to the Moon's environment. These spores could survive in the permanently dark craters where there is stable temperature and protection from radiation. Graham hopes that the Artemis mission will bring important resources like water or carbon that could help microorganisms survive and thrive. However, she also has some counterpoints. The large number of missions to explore the Moon's southern pole could lead to contamination of the Moon's environment. The astronauts' equipment and emissions from spacecraft could inadvertently release carbon dioxide, water vapor, and other gases. These harmful gases could affect the survival of microorganisms in the Moon's dark craters because carbon dioxide is toxic to microorganisms and could hinder their growth. Graham also points out another potential issue, the environmental changes in experiments on microbial life. As space exploration continues to advance, the number of spacecraft traveling to the Moon is expected to increase. Their presence, especially the emissions, could impact the accuracy of studies on microbial life. When spacecraft fly by or land, they could unintentionally alter the environment, releasing chemicals that could distort the results of research on microorganisms' ability to survive. This emphasizes the need for strict management of human impacts during missions to avoid distorting results and protect extraterrestrial environments for scientific research. Based on Graham's input, many agree that life may have existed at the Moon's southern pole but has been affected by human impact. This is indeed a timely and interesting idea. But ultimately, without reliable data, it can only be considered speculation. Even Graham has yet to find evidence to convince skeptics. So, in the future, we must still wait to answer this question. Alongside research on life at the Moon's southern pole, extraterrestrial theories are also attracting significant attention. One of the most popular hypotheses is that extraterrestrial life may have once existed or still exists in the Moon's permanently dark regions. According to this theory, the Moon is not just a dry, barren rock as we know it, but it may have been home to extraterrestrial civilizations long before humanity began to study it. Extraterrestrial theorists argue that traces of alien life may have been hidden by space agencies like NASA. Perhaps this is why, after Apollo, no country has sent humans back to the Moon. Recently, the US wants astronauts to return to the Moon to secure any information they may know about extraterrestrial life. Additionally, there is a theory about the survival of extraterrestrial bases built by aliens or even ancient civilizations from other star systems. Supporters of this theory point to images from spacecraft or satellites that may contain strange objects or inexplicable structures. They argue that these bases are not of human origin but belong to extraterrestrial beings and may contain advanced technologies that we cannot yet understand or access. Finally, there is another theory focused on the biological potential in the Moon's permanently dark regions at the southern pole, where there is a large amount of water ice. It is likely that tiny microorganisms or other forms of life have existed and continue to exist there, which scientists have yet to discover. But wait, this theory is very similar to what scientists are already speculating and researching. It turns out that from the beginning, we have been trying to search for extraterrestrial life based only on physical and biological principles. In summary, although there is no scientific evidence to support these theories, stories about life at the Moon's southern pole continue to attract the public's attention. Nevertheless, these stories reflect humanity's curiosity and thirst for exploration of the unknown in the universe. Let us hope that space missions like Artemis will continue to shed light on many things about the Moon, and maybe in the future, this mystery will be unraveled, offering a clearer view of extraterrestrial life. The Moon's southern pole, with its craters full of ice and frozen water, has recently become a target for human research. Could extremophiles survive there despite the harsh environment? Is the Moon just a dead, cold, empty rock as we once thought? And if life exists on the Moon, what would it look like? Could it provide humans with the opportunity to find new pieces of the bigger picture of life in the universe? Are we truly alone in this vast space? These questions, though unanswered, still flow through us.